again, the goal today is to get into those two exceptions and how to remove electrons. The main goal is removing electrons, but I want to kind of recap most things, and this table lets me recap most of what we've done so far, and then we can finish off with the last new stuff. So you really have to keep comfortable with shell and subshell and orbital. So that's the big thing I'm trying to help you clarify a little bit. So the shell is kind of like Bohr. Okay. They're kind of the rings of that planetary Bohr type model. Okay. It's how far is the electrons on average from the nucleus. So we've got the first shell, the second shell, the third shell. Okay. Then we took this leap into diving into what's inside a shell, where you'd never dived inside that before, and we call those subshells. Now for the first energy level, you only have one subshell. You just have an S. Okay. So there's only one subshell, and S's come in ones. Within an energy level, you can't have more than one S. One type of subshell, just one orbital, and every orbital can hold 2 electrons. Okay. When you're asked about orbitals or how many there are, it's good to think of those orbital diagrams. How many boxes did you make? Okay. In every box, you can do an up arrow or a down arrow. Okay. So we'll slowly build up in complexity, but you know, this nicely see the patterns. For the second energy level, you can have an s orbital, and you can also have p's now, and there are 3 p's. It's a 1, 3, 5, 7 kind of is the shortcut. Okay. We learned all about quantum numbers, but you never really need to use them. You can just use the patterns. Okay. Those 3 p's are coming from the -1, 0, +1. Okay. But that's where you don't have for ML. So how many total orbitals do we have in the second energy level? We've got 1 s and 3 p's, so there's 4 in total. So there's 2 types of subshells, 4 orbitals, and every orbital holds 2 electrons. I'm just going to do the third energy level and stop. The third energy level, we have a new type of S, a 3s, but there's only 1 of them. Okay. We can have 3 p orbitals, they're in the third shell, and now we can have Ds. Okay. So you could go through all the quantum numbers and you get to -2, -1, 0, +1, +2, but 1, 3, 5 just sort of is a nice shortcut to remember how many Ds there are. There's 5 Ds. We had 4 S's and P's in total, so we end up with 9 total orbitals. Okay. 3 different types. The subshell has 3 distinctive types, okay. 9 orbitals in total, and we double the 9 to get 18 for electrons. Okay. So orbital diagrams can get quite large. The third energy level would have 9 boxes potentially in total. Now, don't fill by shell, okay? They fill by lowest energy working their way up, and you have that diagonal strategy, diagonals to figure out how they fill. I'm just going to do a little bit if you don't know what I mean by the diagonals. 1s, 2s, 2p, 3s, 3p, 3d. Okay. They don't fill by energy level. They fill by the diagonals. And you can weave your way through the table to help remember that order. If you keep working up by atomic number, you'll see the same pattern. Now I just put in 10 at the bottom to remind you of the patterns. So to get the orbitals, 1, 4, 9, well, 1 orbital is coming from the shell squared, the 4 comes from 2 squared, the 9 comes from 3 squared. If you take the principal quantum number and square it, you get the orbitals. So you might get a question on a test or quiz, how many orbitals are there in the second energy level? And you could just square it and be done. Or you could remember that there's one s and three p's. So there's a couple ways to get to that orbital count. The electrons are 2n squared. So I certainly don't want to draw out all the subshells. There'd be S, P, D, F, and then I'd have to keep going alphabetic till I got 10 letters. And it's going to go 1, 3, 5, 7, 9, 11. It wouldn't even fit in that box. So I'm not going to write out all the subshells, but the total orbital is just going to be 10 squared or 100. And it's going to hold 200 electrons, 2n squared. So hopefully this can recap some of the patterns and give you a visual of the words shell, subshell, and then orbitals. Again, you can kind of think of orbitals as those boxes in orbital diagrams. There are many fill exceptions for advanced placement chemistry. You just need to know about these two that are in the 3D section of our table, or the first row of the transition metals. Chromium and copper. So chromium, I've pre-filled in some boxes. I'm going to use the previous noble gas to represent the core electrons. So if we find chromium atomic number 24 and find it better be a noble gas of a lower atomic number, so we go over to potassium 19, then jump up a row, argon 18 would be the previous noble gas. So these are referred to as core electrons. They don't move or leave when there's a reaction. I'm just going to do what's referred to as the valence, the outermost electrons. And when you do reactions, these are the ones that can get lost or gained. These are the ones that determine all our chemical bonding, and that's the next unit we're going to do. How do things bond? What gains electrons? What loses them? Or do they share? And what structure do we get? They all come from the valence electrons. So after argon, we've got 4s is the next orbital. So there's argon, and we're in the 4th row of the table, the s block. Okay, and then we're into the d block, and in period 4, it's the 3ds. So how many electrons should I put in? We've already done argon, so we have start with potassium. 1, 2, 3, 4, 5, 6 more electrons are needed to get to chromium with atomic number of 24. I'm going to do it the old way, the not exception, and you're not going to write this down, and then I'm going to show you where the exception comes from. Normally, you would expect to fill the 4s first, and you're not going to write this down because I'm going to erase this. That leaves us another 4. And we would go all spin up. And then we run out of electrons, 1 short of filling the d orbitals. So this is what we expect. When we look at chromium, it's not what we get. We find that chromium is more stable, that 3d orbitals start coming down to almost the same level as 4s. And what we see observationally is that all the Ds have 1 electron. Okay. 1 electron ends up moving from the 4s to have 1 single electron. That stabilizes the atom. What really guides every rule of science is what is the most stable configuration. Okay. The world is going towards stability. It's a little more complicated than this. In grade 12 AP, we'll get into a concept of entropy or disorder. And one of our topics will be that the universe is always getting more disordered. Okay? If you take a deck of cards and you throw them, they're never going to land ace of hearts, two of hearts, three of hearts, four of hearts, five of hearts. They're never going to land ordered. They're going to be all over the place, some black ones, some red ones. Okay? Chemistry does the same thing. Everything in the universe is guiding towards more disorder. That's of lower energy. Okay? So this is what you'd want to put in your notes. This is what we find as the electronic configuration or the orbital diagram for chromium. Okay. One of the electrons that we expect to be in 4s has moved into that empty 3D orbital. Okay. It kind of fits into a bit of a memorized camp. Okay. We see the exact same thing with copper. So we were one away from the middle. We're now one away from the end. Copper's in the same row of the table. So it's proceeding, noble gas is still argon. That represents the core electrons. We use this shortcut because these electrons don't get gained or lost. So we wouldn't end up studying these in bonding. We've got our 4s and our 3ds. You're going to want to do the same thing or jump ahead. I'm going to do what we would expect with copper, with it's 9 over in the D blocks. We have 9 electrons plus the potassium calcium kind of electrons. So we would think it'd be this from everything I've learned. You'd think you'd fill the 4s, which I'm going to change. It'd do all the spin ups and then start doing the spin downs, and there'd be one short from filling the Ds. But it's not what we see when we study copper. Okay, elemental copper that's neutral. Okay, it actually ends up being more stable if one of the 4s electrons goes into 3D. You have to be aware of these two fill order exceptions. So these are hard to predict, but if you way back a few lessons ago, you saw a fill order, something like with 1s, then 2s, then 2p. And sometimes these fill orders are really close in energy. And depending on the particular atom, the fill order, the energies can be so close, that's what's causing electrons to flip from one to the other because they become almost the same energy. Last thing for the unit in the day is removing electrons. It's our last topic. It probably has the simplest rule. We're going to remove from the highest shell first. Okay, and that's our first quantum number. Now I'm going to write out that fill diagram. You could put this in your notes or you could leave it out, but I want the visual. 1s, 2s, 2p, 3s, 3p, 3d. I just keep adding another letter as I drop down a row. 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 5g. This isn't the removing that I'm about to put in. The fill order is our diagonals. But it's not our remove sequence. They're removed, stolen by something else, by the largest principal quantum number first. Okay. So assuming it only went up to 6, okay, you'd start removing 6 electrons first, whether they're S, P, D, F. Okay? Then you're going to move to 5 second. Okay? Then you'd move to 4, then 3, then 2, and finally you remove the principal quantum number 1 electrons. So we're going to do everything we've done the same, just remove whatever the biggest number is. So let's look at iron, the atom, the elemental, and then we'll look at Fe2+. We've got to take away 2 electrons to make it 2+, and then we're going to have to take away 3 electrons to make it 3+. Then we'll do the same thing with copper. So Fe, I'm going to use its noble gas core. So iron's atomic number 26. We're using argon again to represent those core electrons. And we've got 4s and 3d. I'm doing 5 boxes for D's. I'm just attaching them together. This is not one of our fill exceptions. So we're going to fill the 4s first. And then we're going to start filling D's. And let's see, it's 1, 2, 3, 4, 5, 6 over in the D block. So there's 6 3D electrons. So I've got 6 of them. I can't really do that. I'm not supposed to go up and then down right away. I'm supposed to go all up. So that's 1, 2, 3, 4, 5. And I got 1 more, so I have to do a spin down. So that's our atom. First ion that we've done. We haven't done a single ion yet. Argon core, 4s. We have to think of our atom, which is right above it. We have to remove 2 electrons, and we have to remove them from the largest principal quantum number first. So our valence electrons are in 3d and 4s. So the largest principal quantum number isn't those last electrons we added. 4 is actually the biggest shell, the biggest principal quantum number. So we're going to take those away first. This is Fe2+, so we're going to lose 2 electrons. So if we start in 4s, there's 1 gone, there's 2 gone. We're going to take away both of those electrons. That will make it 2 positive. All the 3Ds stayed, all 6 of them. That's the electronic configuration for Fe2+. Now we don't see a stable Fe+. Maybe because just having 1 electron in 4s isn't stable enough, and we don't see Fe+. Okay. We're just going to continue this pattern a little bit and do Fe3+. So now with Fe3+, we have to take away 3 electrons. We're going to take away, there's 1, there's 2, we empty the 4th, and then we're going to jump down to the third energy level, okay? And we're going to take away the D's first. We'd actually start with the furthest letter along first, okay? So we're going to take away the D's. Now, which D are we going to take out? Is it going to be this one, or is it going to be that one? Okay. We'd have to think of how we want electrons in orbital diagrams, and we'd want the most parallel spin would be the most stable. Okay. So the most parallel spin, the same spin, would actually be to remove that electron. Then we'll have all spin ups. I'm just going to take away those excess. So the 3 electrons we're going to remove are this one is 1, that one is 2, and then that spin down will be the third. And we'll have Fe3+. So none in the 4s, up, 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 up. That's Fe3+. Now, a few years ago, one of the AP questions, probably 2018, 2019, was to do Fe neutral, Fe2+, and then they rolled into a Chem 30 oxidation question. Okay. In Chem 30, you'll learn whenever you lose electrons, that's called oxidation. When you gain electrons, that's called reduction. Okay. So the last part. Okay. The AP exam is actually almost easier than your high school unit tests, except for it's on a lot of material. That's what makes AP tricky. So they don't ask these really nitpicky standard of excellence type questions, but you have to remember a little bit of Science 10, Chem 20, and Chem 30. Okay. So I want to try working on this yourself. See if you can do copper. Take 1 electron away for copper plus, take a second electron away for copper 2+, and then I'll summarize these shortly. While you're working, I'm just going to pre-write out all those orbital diagrams, orbital boxes, nice and neat. Okay. So the orbital diagram for elemental copper, I'm just going to fill in from the last slide. It's one of our exceptions. So we only have 1 electron in 4s, and then the 3 Ds are filled. Okay. When you move to copper plus, you're going to have to take away that 4s electron. So that is now empty. None of the Ds moved. Or were removed. Copper 2+, you've now taken away 2 compared to the element. So that 4s would be gone, and then you're going to take away a spin down. Convention is the spin up and the spin down are the same energy. Convention is to remove the spin downs first before you remove the spin ups. So I'm writing in the answer. I'm not filling the electrons in all up and then down. I kind of went box by box knowing the answer. So that's copper 2+. I'll do the electronic configuration of the very bottom one. So it's that argon core. The 4s is empty. So you could go 4s0 or just not write it. So either I'm fine with 3d, and we just do the count, and there's 9 of them. On the advanced placement exams, they give equal points whether you wrote out all of argon or did the notation with the core. I would highly recommend you not do out argon's electronic configuration, because if you make a small mistake, you're just going to lose marks. Okay? You don't gain anything by writing that out. So instead of argon, you could be going 1s2, 2s2, 2p6, 3s2, 3p6. And then do the 3d9. Both of these will get you a point on the AP exam. Why would you want to write out the whole thing when you could use the previous noble gas core, save time, and prevent a mistake? Okay. AP questions are marked binary. So either you've done it correct and you get a mark, or you've not done it correct and you don't get a mark. So we're done the quantum mechanics stuff. Okay, we have a couple more lessons to finish up the whole unit, which is all relating to trends in the periodic table, okay, using our knowledge of quantum. So a few questions for you to work on right now. Can you do the orbital diagrams? Just do the valence only, so do the previous noble gas core, and then the valence for the following atoms, so that would be previous to today, and then their most stable ion, or most common. Now your Chem 2030 periodic table lists your charges by most common first. So if you looked at titanium, which is not here, its atomic number 22, it lists 4+, 3+. The 4+ is the most common, is the most stable. 3+ is less common and less stable. Okay. So use your table, find the most common charge. That will tell you how many electrons you need to remove. So I'll put up the answer for 1C. So the periodic table is your guide for doing that answer. So I've got to do silver, and then silver plus is the most common ion. So silver, atomic number 47, the previous noble gas is krypton. Then I'm going to use the periodic table to guide me into the valence orbitals. Silver atomic number 47, if I go all the way over to atomic 37, rubidium, that's in the 5s block, and then we're into the 4d, starting with yttrium at atomic number 39. So I got 5s, 4d. I'm going to label it kind of once for the atom and the ion, and then I got my 4Ds. Now I'm just going to count atoms, how many atoms silver is over. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 over. I went through 4s, and then it's 9 over in the pass. The 5s is filled, and then 9 over in 3d. Two, 3, 4, 5, 6, 7, 8, 9. Okay. Then I have to take one away. The largest principal quantum number is 5, so I'm going to take away one of those 5 electrons. So we're only going to have 1 left in 5s, and I have not touched the d's. No, there are some other exceptions in filling. We're not going into those, so this is what we would expect using our normal fill rules. I'll just make a comment about number 2. Calcium is 2 away from the end, so it's atomic number 20. It's 2 after an argon core, where scandium is 3 after an argon core. And when you strip away 2 electrons for calcium, all that's left is argon. With scandium 3+, when you strip away its 3 valence electrons, you also just get argon left. And in a future lesson, we'll name the atoms that have the same electronic configuration, so just argon core in this case, are isoelectronic with each other. So argon, calcium 2+, and scandium 3+ are all isoelectronic. They have the same electrons, the same count in the same orbitals. They have different proton numbers, so there'll be some slight variations, but they still are isoelectronic, same electron count. Okay.